Hey guys, so we're going to start Unit 2 by looking at a review of system of equations and looking at the different ways of solving system of equations. So just as a quick review, when you think of a system, you think of more than one thing working together. So you might have at home a stereo system where you have a speaker and a TV connected to the TV, connected to a DVD player, etc. You might have a computer system that is set up to connect your monitor and your desktop and your computer and speakers and router, etc. So when you have a system, it's just more than one thing working together. And when we have a system of equations, we have a set of two or more equations that are working together, and they contain two or more variables. So when we talk about the solution of a system of equations, we're talking about an ordered pair, x comma y, so a point, that satisfies each equation in the system and makes them true. So it has to work not only for one equation, but for all of the equations that is in that system. And usually when we have a system, when we have a set of something working together, we have this big brace, kind of like the piecewise function that groups them, telling us that they are working together. So in example 1, I want us to start by determining whether the ordered pair is a solution of the given system. So remember, in order for it to be a solution, it has to satisfy both equations. So let's substitute our ordered pair into the first equation. 5, 2, I'm going to substitute it into 2/5 times 5 minus 2, and I'm going to see if that's really equal to 0. So when I multiply, I have 2 times 5, which is 10, divided by 5 times 1, so 10 divided by 5 is 2, minus 2, and we can see that indeed it is equal to 0, and so this ordered pair 5, 2 is a solution to the first equation. But in order for it to be a solution to the whole system, it's got to satisfy both equations. So let's check the second one. So 3 times 5 minus 2, does it really equal 13? That's 15 minus 2, and that is 13. And so because we have an ordered pair that satisfies both equations in my system, this is a solution to the system of equations. Go ahead and pause the video for a minute and check B to see if the ordered pair -2, 2 is a solution to that system. And I'm going to do out the work, and then you can skip forward to see if you got it, and if you got it, you can move on from there, and if you didn't get it, you can rewind and see how I did it. So I'm going to substitute it in. -2 minus 6, is that really equal to 4? Oh, that should be a +2, sorry. Your y is 2, so -2 plus 6, that is 4, is equal to 4, and that is correct. So now let's check the second one. Be very careful of the second one because you got a negative x, so I have a negative, and my x is -2, so negative of -2 plus 2 is equal to 2. Negative of -2 is really 2 plus 2, and we see that there is a problem. On the left side I have 4, and on the right side I have 2. So even though this point, this ordered pair, is a solution to the first equation, it is not a solution to the second equation. So this is not a solution that is a solution to the whole system. Okay? So when we are thinking of the graph of a system of equations, let's look at how we would classify a system of linear equations. Usually when we have, going back, if I were to graph these, okay, they're in standard form, but they're going to be two lines. And the solution is this, meaning that's where the two lines are going to intersect, because it's got to be a point that is on both lines. So anytime you have a system of two linear equations, two lines, you could have three possibilities. Possibility number one, you could have intersecting lines. So for example, you could have one line. I'll try to draw a line. Okay, here we go. So let's draw a line that has a y-intercept of +2, and then I'm gonna go down 3, right 2, say that's the slope. Okay, and then down 3, right 2. I'm just gonna draw my line. Okay, and then let's have another line that has a y-intercept of -3, and then my slope, I'm gonna go up 1 over 1, up 1 over 1, up 1 over 1, and I'm gonna draw my second line. Here we go. Okay, so if you have intersecting lines, then we can see that the two lines intersect at this one point right here, and that is the solution to your system. Okay, so the solution in this particular case is 2, -1. The point 2, -1 is a solution to both equations because it's a point that is on both lines, is where they intersect. When a system of equations has a solution, we can classify it using vocab. We can say that this system is consistent. Some vocab, new vocab here. Consistent, meaning that it has a solution. Okay, consistent, meaning that it has a solution. And then we say that if it has exactly one solution, we have another term for it. It's consistent, and it is also independent. Meaning that it has exactly one solution. There's only one solution. It only intersects one time, and that particular solution in our case is 2, -1. A second scenario is you could have two lines that overlap. They're coinciding lines, meaning that they're practically the same line. So if I draw my first line, any line that you like, doesn't matter, just draw a line. And here we go. And let's say my second line, if I draw my second line, overlaps it completely. It's basically the same line. I want it to overlap completely. Alright, it's basically the same line. So if you think about that, how many points would these two lines intersect? If they are the same line, since they basically intersect at every single point, and so in this case, we have infinitely many solutions. There's too many to name. Infinitely many solutions. Okay, and we're gonna say that this line, this system of equation, the system is consistent, again, because it does have a solution. Consistent means it has a solution. And we're gonna say that it is dependent instead of independent. Now we have dependent, which means it has infinitely many solutions. That's how you would classify the system. And then the last scenario, you could have two lines that are parallel. So from geometry, you know what parallel lines look like. I'm just going to draw any two lines. Yours don't have to be exact, so in your notes, just draw two lines that are parallel. Okay, so if they are parallel, remember the marking that we can put on there from geometry that indicates that they are parallel. We know that parallel lines will never intersect, so in this case there is no solution. And there's actually a symbol for no solution. It's a little circle with a slash through it. This means no solution because they will never intersect. So instead of consistent, which means it has a solution, we're just going to say that this system is inconsistent. Inconsistent, meaning it has no solution. Okay, and then we don't have to talk about whether it's independent or dependent because it doesn't have a solution. So anytime you have a system of two linear equations, two lines, it's going to be one of these scenarios. You're either going to have exactly one solution where they intersect. You could have no solution when they're parallel lines because they'll never intersect each other. Or it could technically be the same line, in which case they overlap everywhere and you would have infinitely many solutions. So let's take a look at different ways of figuring out which one it is. So there are three different ways to solve a system. We're going to go through all three ways, and you could use any one of these ways to solve for a system. So the first method is to solve by graphing. So we can graph the two lines and see on the graph where they intersect, and I should be able to see my solution, right? So the first equation, y equals negative 3x plus 4, is nicely written in slope-intercept form for us. So I can go ahead and graph. So my y-intercept is at 4. And my slope tells me to go down 3, right 1. Negative 3 is negative 3 over 1. Negative 3 over 1, negative 3 over 1. And I have this line. I'm just going to sketch mine out. Okay, and then the second equation is not written in slope-intercept form. So if you want, you could rewrite it so that it is in slope-intercept form. By isolating the y, let's add 3x on both sides. Y equals 3x plus 2. Okay, we're going to put the 3x first so that it looks like y equals mx plus b when you're graphing it. So I know that my y-intercept is at 2, and my slope says to go up 3, right 1. Okay, and I don't have any more space to go up 3, right 1, so I can go in reverse and get a few more points. And I'm going to sketch my line. Okay, and the point of intersection is right here. This is the point where they intersect. Now the problem with this is it's a little bit harder to see exactly where that point is. And that is why when we're solving by graphing, this method is the one that we don't usually rely on, because it's nice when the two lines intersect and it's right in the corner of a square where I can tell exactly what that point is. But sometimes you would have lines that intersect and it would be very hard to see exactly what that is. It looks like my solution, the point, the ordered pair, the y value looks like 3. The x value though, I'm not exactly sure what that is. Okay, so if solving by graphing doesn't give me an exact answer, you could guess. I'm gonna guess that it's around 1/3. Okay, but it's hard to tell. Alright, so I don't rely on solving by graphing. A more accurate way to be sure we get the exact answer all the time is to solve algebraically by using the second and third method, which is by substitution and elimination. So let's look at method number 2. We can solve the exact same problem using substitution. So this is the same problem that we graphed before. Let's now solve by substitution and see if we get that same answer that we can be more sure of. Okay, so in substitution, our goal is to substitute one equation into the other so that instead of having two equations, we have one equation with one variable. Okay, individually, I can't solve these because I have two unknowns, but if I can combine them into one equation with just one variable, then I can solve for that variable. So when you're solving by substitution, first thing you gotta do is to get one variable by itself on one side of the equation. Solve for one variable. In this case, y is already by itself, so I know that y is equal to negative 3x plus 4, and I can substitute this into the second equation in place of y. So I'm going to go ahead and do that. So the second equation, negative 3x plus, instead of y, I know that y is equal to negative 3x plus 4. So I'm going to substitute that in, equals 2. And then now we have an equation with just one variable. So now I can simplify. Negative 3x minus 3x plus 4 equals 2. Combine like terms, negative 6x plus 4 equals 2. Minus 4 on both sides. Negative 6x is equal to negative 2. Divide both sides by negative 6. I have x equals, negative divided by negative is a positive, 2, 6 is really 1/3, and so x is 1/3. Once you have one variable, you can take this x equals 1/3 and substitute it back into either one of the original equations and solve for y. Entirely up to you which one you want to substitute it back into. So I'm just going to substitute it back into the first one. Y is equal to negative 3 instead of x. I'm going to substitute it with 1/3 because I now know x is 1/3 plus 4. Okay, so when you simplify, you have y equals negative 3 over 3 is negative 1 plus 4. Y is equal to 3, and your answer is always an ordered pair. Is the ordered pair 1/3, 3. Okay, if I were to graph these two lines, which we did earlier, the two lines will intersect at the point 1/3, 3. So if I go back, it looks like I guessed correctly. But this I had to guess, and I won't always guess correctly. So sometimes graphing would be easy if you can see the point exactly, but sometimes solve by graphing doesn't always give you the most exact answer. So I would rely on the algebraic method. Okay, so give the U try on the right side, give that a try, and then pause the video, give that a try, see if you can get the right answer, skip forward. If you did, then you move on, and if you didn't, then rewind back and see how I did it. Alright, so in this second problem, when we're doing substitution, the first thing we want to identify is which variable is it the easiest to get by itself. I could try to isolate this x, then I would have to move the y and move the 3, right? I could solve for this y, I could solve this y, or I could solve for this x. You just have to pick one equation and get one variable by itself. I think the easiest one to get by itself, to isolate, is this y, because all I have to do is move the 3x. So I'm going to start with that. I'm going to start with the equation 3x. Use a darker green so you can see it better. 3x plus y equals negative 2, and I want that y by itself. So I'm going to minus 3x, and y is equal to negative 2 minus 3x, or negative 3x minus 2, entirely up to you how you want to write it. We're not really graphing here, so we don't necessarily need to put the x term first, but you can if you want to get into a habit of doing that. Okay, so now that I have the y by itself, I'm going to go ahead and substitute it into the second equation that I haven't used yet. So you have to use both equations. I'm going to replace the y in the second equation with negative 3x minus 2. So 2 times negative 3x minus 2 minus 3x is equal to 14. Now I have an equation with just x's, and I can solve for x. So let's distribute negative 6x minus 4 minus 3x equals 14. Combine like terms, that's negative 4 minus 9x equals 14. Add 4 to both sides. Negative 9x is equal to 18. Divide both sides by negative 9. And x is equal to negative 2. Okay, and then again, once you've solved for x, you can put it back into any one of the original equations just to be safe, to check to solve for y. So either one that you like. So I'm just going to pick the first one. So the first one is 3 times, instead of x, I now know it is negative 2, plus y equals negative 2. Negative 6 plus y equals negative 2. And then we can add 6 on both sides. And y is equal to 4. So the point that is a solution to both equations, the solution to this system is the ordered pair negative 2, 4. If I were to graph these two linear equations, I would have two lines intersecting at negative 2, 4. Okay. And then certainly if you want to substitute negative 2 in for x and 4 in for y into both equations, you can check your work and see if you got it right. If it makes both equations true, then you know you did it right. And then the last method of solving a system of equations, a second algebraic way, so method number 3, is by something called elimination or combination. And the goal of that is to eliminate one of your variables by combining the two equations, either by adding or subtracting them. So in this case, the first thing you want to decide is, do you want to eliminate the x's or eliminate the y's? And in order to eliminate them, we need opposites, right? So, for example, if I want to eliminate the x's, then I would need these to be opposites. Then I would say, all right, the second equation has negative 3x. If I can make the top one have positive 3x, then I can eliminate by adding the two equations. And so the first thing we gotta do is decide which variable you want to eliminate, in which case I'm going to eliminate x. It doesn't matter which one. And then the second thing is to create opposites. So I'm going to do that by multiplying the whole equation by 3. Okay, you must do it to the whole equation. So I'm going to rewrite this. Now I have 3x plus 2y, distribute the 3x plus 6y equals 33. And then the second equation I'm going to rewrite the same way. Negative 3x plus y equals negative 5. I didn't change that. And then what we're going to do is we're going to add these two equations. And when I do that, notice that positive 3x and negative 3x adds to 0. It cancels out. 6y plus 1y is going to give you 7y, and then 33 plus negative 5 is going to give you 28, and then we divide by 7. We have successfully eliminated my x's, and we can solve for y. We have y equals 4. Okay, once you use elimination to solve for one variable, then you substitute the 4 back into any one of the original equations to solve for x. So back to substitution. I'm going to pick the first one. So the first one, I have x plus 2 instead of y. I'm going to put in 4 equals 11. X plus 8 equals 11, minus 8 on both sides. X is equal to 3. And so my solution to this system is the ordered pair 3, 4. If I were to graph these two lines, they would intersect at this one point, 3, 4. Similarly, if you had wanted to, you could also have decided I'm going to eliminate my y's. So if you did that, let me rewrite the original problem. If you want to eliminate your y's, then you're going to need these to be opposites. So what we can do is we can multiply the whole second equation by negative 2. Okay, then I would have the first one would stay the same. The second one would become 6x minus 2y equals positive 10. Gotta multiply the negative 2 to every single term. And then when I add them, 2y and negative 2y would cancel out. And I would have 7x equals 21, and x would equal 3. And I would have that first variable. So it doesn't really matter which variable you solve for first, both in substitution or elimination, whichever one is easier, okay? And then once you have the 3, you can substitute that back into any one of the original equations and solve for y. So I want you to use these as examples and work on the homework, which is more practice on substitution, elimination, and solve by graphing.